Hello, my name is David Schultz. Welcome to Our Earth, its climate, history, and processes. In this lecture, we want to know about the interior of the Earth. Specifically, we want to ask the question, how do we know all about the interior of the Earth if we've never been there? As I've mentioned, the deepest holes drilled into the Earth only go down to about 12 kilometers. So how do we know what the internal structure of the Earth is if we don't have any direct evidence? There's several things that tell us what's going on, and I want to tell you about them now. First, we have data from seismograph stations around the world. And what this does is it's a little bit like MRI at the hospital, where they send radiation through you, see how it penetrates, and then construct the interior based on all the different ways that radiation interacts with your body, the different densities of material. The same thing happens with with the seismic data. We can understand the changes in the composition, the density, whether it's solid or liquid, all based on the speed of arrival of these seismic waves at different parts of the Earth. So that's the first piece of evidence. The second is we know about the core because we see it being very similar to iron nickel meteorites that date from the time of the Earth's formation. These iron nickel meteorites are basically fragments of asteroids that of a planet that had similar differentiated interiors and has since been broken up. So we were able to see the different parts of this planet from these meteorites. The third piece of evidence is that if we were to take the density of the Earth's crust and assume that the Earth had this density throughout the entire Earth, then we would come up with a mass of the Earth which is much lower than is observed. And by observed, I mean how it interacts with the other planets through Newton's laws of gravitation. So the essence of seeing how our Earth interacts with other bodies tells us that the Earth must be denser in the interior of the Earth than it is on the crust, so that we get a mass that is consistent with these laws of gravitation. The fourth thing are the ophiolites. These are sequences of upper mantle and crustal rocks that, due to subduction and then being thrust up onto the continents, illustrate what the upper part of the mantle and the lower part of the crust look like. Places that we don't have any direct evidence. Yet another evidence for the internal structure of the Earth derives from laboratory experiments. We can take rocks and minerals, expose them to the high temperatures and pressures that we find in the interior of the Earth, and see how they change. One mineral in particular is spinel, and we know that spinel goes through several different phase changes as you go deeper and deeper into the Earth. These phase changes correspond to differences in seismic wave speeds that then tell us about how the interior of the Earth is layered. Another piece of evidence are what are called xenoliths. Xenoliths are pieces of rock from a magma chamber, from the walls of the magma chamber, that are then incorporated into the magma and then brought to the surface. So when the magma cools, we see rock of one type, and embedded within that rock, we see fragments of what's called the country rock, this rock surrounding the magma chamber. So we may be able to see what the composition of the walls, the material surrounding the magma chamber, is. The last piece of evidence I want to give you about the internal structure of the Earth comes from the magnetic field. The Earth's magnetic field, as we've talked about before, originates within the outer core, the region of the Earth that's molten and is composed of 85% iron. because this fluid is in motion, it produces a magnetic field, and this magnetic field we see on the surface of the Earth and the exterior of the Earth. So we know then, by the very existence of this magnetic field, that there must be this liquid part of the core. So that's a lot of evidence that tells us about the interior structure of the Earth, where we don't have any direct observations of it. So I think it's really important to understand as a science how we get information about places that we simply cannot go, but can nevertheless say quite a bit about.